Okay, welcome back, everyone. Hope you had a good weekend. We've been talking about PCA, and this is a bit of a summary. So we start with data of dimension D, and our goal is to squeeze it down. These are different samples in our data set, and we squeeze these down to samples of dimension R. And the way we do that is we first remove the mean of all of our samples. We call them X tilde. Then we compute the covariance matrix using those X tildes. And then we can do an eigendecomposition of the covariance matrix. And from that, we extract the R eigenvectors corresponding to the largest eigenvalues, and we use those to construct the coefficients z hats. Those are now of dimension R, which is a number of our choosing. And then if we want to construct our approximation from those, we basically bring these R-dimensional things back into the D-dimensional world by multiplying by this tall matrix, and then we add back the mean, and then that gives us our approximate data samples. And we have some pictures. If we have three-dimensional data and we want to reduce it to two-dimensional data, that means that within this three-dimensional space, we need to find a two-dimensional plane that gives us the smallest projection error of all of our data samples. And if instead we want to reduce this to a one-dimensional space, then we would find the line in this three-dimensional world that gives us, again, the smallest projection error. So those are just some examples of PCA. Any questions about PCA? Okay, so then we talked about there's a way to measure the performance, which is very similar to R-squared that we used in linear regression. The only difference is that instead of looking at the target variance, you look at the sum of the variances of all your features, which is also, you can express that using the trace of the covariance matrix, Q. And it boils down to this expression where you sum up the capital R eigenvalues versus the D of them. So this ratio is going to be some number between 0 and 1, and that's this proportional variance. So the closer to 1 this is, the better the approximation. Okay, and then the last thing we were talking about was the singular value decomposition, which has many, many uses. We'll be applying it to PCA, but it's good to know about this anyway. So you can start with any matrix X, and you can decompose it into a square matrix, a matrix S that's diagonal of the same shape as X, and another square matrix. And those square matrices are orthonormal, so all of their columns and rows are orthogonal to each other, and they're all normalized to unit norm. And then this diagonal matrix S contains non-negative numbers that are ranked from biggest to smallest. And another way to think about this SVD is that if you apply X to a vector by left multiplication, this SVD says you can equivalently rotate somehow, then scale those rotated coefficients, and then rotate again. And for any linear operation X, you can always think of it as rotation, scaling, and rotation. Okay, so that's the standard SVD. These matrices, U and V, are always square. S is always the same dimension as X. But then there's another version of it that strips out the columns of U and the rows of V transpose that do not directly contribute to X because of all the zeros in this matrix, and it just gives you the ones that do. So in this case, UR will be a tall matrix, VR transpose will be a wide matrix, and X is going to be square. And furthermore, this S, that's again diagonal, all of its coefficients are actually positive. And as a result, this S is invertible, whereas this S is not square, so it can't be invertible. Also, its diagonal could contain zero value entries, whereas this one cannot. Okay, so these are just two different ways to unpack a matrix S into some factors with a lot of useful properties. You can do this for any matrix. So now we're going to come to see why this is useful for PCA. So let's say for PCA, we always start with our mean removed data matrix, which has n samples of dimension d. And if we think back to what we did to compute PCA, we first computed the covariance matrix of our data, and we can do this directly with our mean removed data matrix just using this scaled product like this. And we also know that, or we have been writing the eigendecomposition of Q as V lambda V transpose. And so this V, again, is an orthonormal matrix. And the lambda is a diagonal matrix with non-negative entries. And we have been saying that we're going to make sure that those eigenvalues are sorted. Okay, so this is what we use for PCA. And then the final step of PCA is basically instead of using all of those entries, all of the eigenvectors and values to get an exact covariance matrix, you just truncate this, you only use the largest R of them. And then you get an approximation of Q. Okay, so that's kind of what we do for PCA. So now let's take a look at the SVD, the standard SVD of X tilde. So from the previous page, we know that we can write this as the square U matrix times S times the square V matrix. And if we then compute the covariance matrix using this X, so we just plug this into that expression, then we have, this is our SVD, this is our SVD transposed, and immediately we see that we have U transpose U, but because these are orthogonal, this boils down to the identity matrix, so you don't need to worry about this. And then we can maybe move this 1 over n inside here, and when we take a step back and look at what we essentially have expressions of the same exact form. So we have orthonormal square matrix, that's what this is too. And in the middle, we have a diagonal matrix of non-negative entries that are sorted. That's exactly what this is. So as a result, now just visually we can see that when we compute this SVD of the X tilde matrix, we automatically get what we need for PCA. So the V matrix we use for PCA is exactly the SVD's V matrix, and the eigenvalues in PCA are just the squared singular values divided by n. So we can do this. So one advantage of doing this computationally is that actually this step of computing Q takes a lot of computational effort, especially when this matrix X tilde is large. Just computing these takes a lot of effort, and then you have to do the singular value, then you have to do the eigendecomposition. So when you do this SVD method, you never actually compute Q. You just work on X tilde directly. So you kind of bypass this whole step. And you just get what you need directly, which are these two quantities. So that gives you a computational savings. Okay, any questions? Okay, so this is one of the ways you can use SVD. But actually, if you think about it, there's a better way to do this, because when we're doing PCA, we only keep the top capital R singular vectors. We don't actually use all of them. And the number that we keep is definitely going to be equal to or less than the rank of our matrix R. And the rank is, the biggest that could be is the minimum of the dimensions of x tilde, n and d. And typically, for PCA, we choose a rank, an approximation rank that's much, much smaller than the rank of the matrix. So this means that if we use the full SVD to compute this square matrix, we would basically be throwing away most of the columns and keeping only capital R columns, which is very small. Maybe over here I should actually write j equals 1 to, what do I want to write here? I guess D, just to emphasize the similarity. Yeah. Okay, so basically, we can instead use the economy SVD, because the economy SVD computes as many as are in the rank, and then we can truncate that down to R. So economy SVD is just a shortcut to what we actually need for PCA. So the final procedure then to run PCA, you do the economy SVD on your mean and move data. You basically ignore this U matrix. This V little r, you keep the first capital R columns of it. Capital R is your choice. Once you have that, you can compute your coefficients. And if you want to reconstruct the approximation, you multiply your coefficients by VR and add back the mean. Okay, so that's basically how we can use the economy economy SVD as a robust and fast way of computing PCA. Right. Any questions? Yes.
So, is it possible to quantify the performance difference between the two, like the economy SVD versus the normal SVD?
Performance in terms of complexity or accuracy?
In terms of computational cost, rather than. Although I suppose you can't really consider one without the other. So.
Well, yeah. So in an ideal world, they would give you the same exact answer to these. Now, to actually do the economy SVD, there's a bunch of different algorithms that could be used. And which one you use depends on, for example, if you have a sparse matrix, you're going to use an iterative algorithm. If you have a dense matrix, you can use other things. So it really boils down to which algorithm you want to use. And it also boils down to some extent to how big R is, because if you only want to compute like the first two vectors, there's sort of a shortcut where you can compute the largest one using the power method, and then you strip that off by just removing a rank 1 component, and then you use the power method to get the second one, and that might be faster than running some fancy, yeah. So which algorithm you use affects the runtime, and that one depends on the nature of the data you have.
It'll be situational.
Yeah.
An engineering choice.
Kind of. It might depend. So if you just use like the off-the-shelf solver, I'm not sure. You might be able to control it somewhat, but if you code it yourself, then you have all the flexibility that you would ever want.
Okay.
Yeah.
Thank you.
Sure. Okay. All right. Any other questions? Okay. So all right. So the last math slide is, what if we want to standardize the coefficients? So the idea here is, let's say we've done our dimensionality reduction for our data set, and we have reduced all of our full dimensional xi samples to these lower dimensional zi samples. And now let's say we actually want to do something else with them. So I'll show you some examples of classifying some targets using those PCA samples. So of course, you need the target data if you want to do classification, so just assume we have that. Well, we know that a lot of our classification methods, not all, but a lot of them like the data to be standardized. If we're doing a tree method, we don't really need that, but if we're doing any regularized method, feature selection, anything like that, we want standardization. And so let's take a look at our PCA coefficients to see if they're standardized. So remember that what we want of them, which is maybe not what we have, is we want that the sample mean of the z coefficients equals 0, and we want that the sample variance of each coefficient j equals 1. Another way to write this is if you look at the sample covariance matrix of the z coefficients, then all the diagonal elements of that matrix, which are these sample variances, they should all be equal to 1, so that the diagonal of this matrix is the ones vector. So those are the things that we know we want. That's how we standardize data. We want 0 sample mean, unity sample variance. But, okay, this is what we want. But this is what we have. We have this. Okay, so let's take a look at our actual z hat. So we know that by definition, z bar is just this sample mean. So let's plug in for zi. Let's plug in exactly how we made zi. We multiplied the mean removed x tilde I by this matrix. Okay, so by linearity, we can move this matrix multiply out there, and then we have this sample mean of our mean removed data, and yes, that thing is 0. So we multiply this matrix by 0, we get 0. So that's great. So our data, our PCA coefficients, these guys are centered, meaning sample mean equals 0. So that agrees with this. Let's take a look at this. Is this what we have? Okay, so the covariance matrix of Z, this is the sample covariance matrix, just our outer product averaged. And what we can do again is we plug in this expression for Z, and for Z tilde, we move the sum inside, and we get this. And now we see, oh, this part is actually the sample covariance matrix of our coefficients X. And so we called that just plain Q before. But then one more step, let's plug in the SVD of Q. We know that that takes this form. And immediately we can notice a simplification. So this is a tall matrix whose R columns exactly match the first capital R columns of this. And because of a property of the SVD and the eigendecomposition, we know that basically because all these eigenvectors are mutually orthogonal, that this matrix has a very specific form. It's like the identity matrix followed by a whole bunch of zeros. Because these guys are, they're orthonormal, mutually orthonormal with the first capital R vectors in here, and then they're all totally orthogonal to the rest of them. So that's where you get this. So at the end of the day, when you multiply on both sides by this, all that does is it extracts the first capital R coefficients of this diagonal matrix. And so we finally get that QZ is this diagonal matrix. And what we see is that this is what we want. We want that the diagonal of that equals the ones vector, but instead the diagonal of this matrix is going to be that vector. So these coefficients are probably not going to be 1 for all terms. So there's an easy fix. If you want a standardized version of z, make this new vector, which I'll call z tilde. All you do is you scale each coefficient in zi by those numbers. So the first coefficient, you divide it by S1 and multiply it by square root n. And then if you notice, what happens is when you look at the covariance matrix of these guys, this will inflate the variance by a factor of n, which will cancel this. And then this will multiply the variance by 1 over s squared, which will cancel this. So this scaling gets rid of this and turns this into just basically an identity matrix or one's vector on the diagonals. So the moral of the story is that if you want to standardize your PCA coefficients, it's very easy. You don't need to do anything to center them, but if you want to scale them so they have unit mean, you just scale them by this sequence. And at that point, you could use any method for classification or regression or whatever you want that would like the data to be standardized. Okay, so that's all for the math for now. Any questions on that last part? Okay, so now let's do something a little more fun. Let's apply PCA to some face data. So we're going to use a data set, it's 20 years old or so, labeled Faces in the Wild. It's a set of face images that are pretty small. They're 50 by 37 pixels. Convenient for doing experiments on cheap laptops, but modern face data sets will have much bigger faces and they'll be color. So just as a note, and so let's see what happens if we apply PCA to these. So we first load the data. The full data set has 13,000 images, but we are actually going to trim this down to 1,288 images by requiring that we have at least 70 faces per person in the data set. And these face images are from news stories in the 2000s. And so the sort of people that you'll find, I think this is ranked from most common down as people like George W. Bush, Colin Powell, Tony Blair, Donald Rumsfeld, and so on. And it turns out, yes, actually there's only 7 different people in the data set. So if we're going to do classification, then we're going to classify, according to these different 7 categories. Another thing to note is when you look at the actual pixels, they are numbers between 0 and 1, where black would be, let's see, in this data set, black is going to be 0, and white is going to be 1, and gray is numbers between 0 and 1. And that's how most grayscale image data is normalized. Sometimes this will go from 0 to 255 as an integer, but in this case, these are floating point values from 0 to 1. Okay, so that's the data. So how do we apply PCA? First, we compute, and by the way, similar to what we saw with MNIST, even though these are 2D images, in the data set, you basically rasterize them, so you make one long vector out of all these pixels. And so now you're going to have the image size gives you 1,850 pixels. So there's 1,850 features for every sample, and there's 1,288 samples. Okay, so that's what the matrix X is. So we have a matrix X, which is going to be 1,288 by 1,850. So this is one of these kind of not very common situations in machine learning where the number of samples is actually less than the dimensionality. Usually in machine learning, you have more samples than the dimensionality, but once in a while you have less. Okay, so to apply PCA, we're going to use this SVD method, economy SVD. So the first step is we compute sample mean. We have our X matrix. We just do the mean of every column. And then we subtract that using Python, our NumPy broadcasting. We get our zero mean X matrix, like X tilde. We do the SVD, tell it full matrices equals false. So then it does the economy one. And when we look at the shape of the V transpose matrix, it's exactly what we expect. So we have like a number of samples. N this way is 1288. This is D is 1850. And the economy SVD gives us a square S matrix. And we expect, let's see, I didn't draw this very well. This data, we said actually this is wide. So let me redo this. So we have sorry. Okay, this should be square. This should be square, and this should be wide. Okay, so this dimension is the rank of the data, little r. This dimension has to be D. This dimension should be the rank. And then this dimension has to be N, rank. Okay. So the rank of the data matrix is at most 1288 because this 1288 is the minimum dimension of this matrix. It could be that there are redundancies in the data, so sometimes the rank of this matrix could be less than the minimum dimension, but in this data set, we know that it is full rank because when we compute these quantities, we notice that economy SVD does give us 1,288 rows, which means that's the rank of our matrix. So it's a full rank matrix. And this is our V transpose over here. V transpose SU. Okay, and the V transpose matrix has this wide shape, which is exactly what we expected. Okay, now we also get a vector of singular values. That's also going to be 1,288 elements in that vector. And we can compute our eigenvalues just by squaring our S vector, again, NumPy broadcasting, divided by the number of samples in our data set. Now we know our eigenvalues in our, for PCA. And to do this proportion of variance, we can just do a trick with the cumulative sum, where we basically, for every choice of R, that's going to be one term in this cumulative sum. And we can see as you vary R, this POV gets closer and closer to 1. So it won't get all the way till 1 exactly until the very last term, but these eigenvalues here are very small. So you don't get that much from including them. So where you get a good approximation, it's hard to say. Somewhere in this region, the approximation seems almost perfect. Maybe at like 600, it's, I don't know, visually it looks like it's almost exactly 1. So that suggests that if we're going to be compressing our data, depending on how much compression we want to do, maybe somewhere in this range is good because that's going to do a pretty good job of compressing the data in terms of like reducing the dimensionality by a factor of 3, but then keeping most of the variance in the data. Okay, so I wrote 400 here, but yeah, somewhere in this range is probably a good choice. All right, any questions on PCA? So now we have our eigenvalues, and we have our eigenvectors as the rows of this V transpose. Okay, so let's look at some pictures. So here we have the PCA approximation if we use one component, so capital R is 1. If we use 3, it's better, right? If we use 10, a little better. If we use 30, it's better. So as you keep using more and more values, the face gradually gets to the ground truth face. And here at 300, you can see it's not perfect, but it's pretty good. And so maybe this is good enough for classification, because these maybe from that kind of approximation quality, you're able to tell, recognize whose face it is. But as you would imagine, like if you're trying to recognize faces down here, probably not going to work because they all kind of look the same. Okay, so now maybe even more interesting is to look at the eigenfaces. The eigenfaces are those principal components. But of course, there's also the mean face. So remember that this is sort of like the foundation on which the eigen approximation is built. So in fact, if you want to use 0 eigenvalues, then you'd be approximating all your data samples by the mean face. And the mean face looks kind of how you'd expect. You don't have, there's no pure black here. There shouldn't be any pure white either because there's averaging across all the data samples. So while some of the individual data samples might have, exactly 0 pixels, for example, in the corners, and maybe exactly 1 pixels depending on how they're normalized. Once you look at the average, you're not gonna see that. So that's kind of what describes the mean face. And here is the eigenvector. This is the principal eigenvector, the most important eigenvector in terms of explaining the data. So if you're going to do a one-dimensional approximation of all your faces, you're going to have the mean plus a scalar value times this image. So that's apparently the best thing to do in terms of minimizing, RSS is one-term approximation. You're going to be basically using that. Does that make sense? So just a scalar value times this, and that's your single coefficient that's going to describe and differentiate all the different samples in your data set. It's just, you've boiled it down to one number, and then that one number is used to scale this image, add it to the mean, and that's how you get the one-term approximation. So what is it doing? Well, you can see it's okay, so also the color coding here. So, trying to remember how we did this. I think, yes. So I tried the color map on these is the same in the sense that black is, the value 0 in the data is black, just like it is over here. The value 1 would be white, but now we have negative numbers. Because we're using PCA, we can have negative numbers, right? So we need a new color. Because here, when we're plotting faces, all our data is non-negative. It goes from 0 to 1. We use black to white. Now when the data goes negative, how do we plot that? So I just chose red. So the more negative it is, the more red it is. So when we look at this, it's sort of interesting. Most of these pixels are red, and then a few of them are closer to black, but that's what we get. So somehow that is like the most important thing to modify this with, if you from the purpose of minimizing RSS. Okay, not very insightful, but the next one is a little bit more insightful. So if you're allowed to add one more coefficient, you end up using this eigenface. And you can see that this one is negative here, 0 in the middle, and positive here. So this one accounts for the fact that some of the faces are pointing one direction, some of them are pointing in the other direction, which affects the lighting. So like this has brighter on this side, whereas this brighter on that side, and that's what this is controlling for, is the lighting from left to right. And then this next one, you can see that this is sort of, this is modulating like the lighting in these particular corners. You also see that there's some slight variation in like the eyes, other facial features. But as you go this way, you just get stranger and stranger building blocks. But these are all the building blocks to construct these approximations. So it's kind of neat to look at. And this is just the first 6 of them, whereas here we're using 300 of them. Okay. So is this making sense, the eigenfaces and the visualization, what PCA is doing? Okay. All right. So now let's try face recognition or classification. So the motivation for using the PCA coefficients is that for a lot of our classifiers to train them, it takes longer if you have more coefficients. And just to make things very easy, where did I write it? Oh, somehow I might have forgotten to write it on this page, but we're going to use XGBoost. The nice thing about XGBoost is that it works pretty well without any parameter tuning. So that's just a way to avoid like that whole step. Let's just do PCA to trim down the coefficients and then give it to XGBoost, and then let's look at the performance and the complexity of XGBoost versus different approximation ranks, capital R. Okay, so how do we do this then? Well, as we know well by this point in the semester, we do a test train split on our data. We do have labels. Remember, we now know the owner of each face, up to 7 different people. So we do our test train split. Because the faces are not super well balanced, we'll do the stratified split, and we'll do 3/4 for training and 1/4 for testing. And okay, so then what do we do to the training data once we have it? We have to compute the mean, and then we subtract the mean from the training data, and then we do our SVD, basically giving us the PCA quantities we need. This is actually doing it for all ranks simultaneously, because the SVD gives us all the different eigenvalues, and then to compute the Z coefficients, we take our training samples, multiply them on the right by V transpose, and then another transpose to cancel this transpose. And then here's the standardization step. Divide by the eigenvalues and multiply by square root of n. Okay, so we have now our standardized data. Note for XGBoost, we didn't actually need to do the standardization because we know that it's a tree method and trees don't care about data being standardized or not. But I put it in here just as a demonstration in case you wanted to use this with a different classifier. Okay, so we've processed our training data. Now we have to do our test data. But here's an important thing. All the processing that we do to the test has to mirror exactly the processing applied to the training. So when we do our mean subtraction, we are not subtracting the test mean. We're subtracting the training mean. We could have computed a test mean and subtracted it, but if we did that, then our test data is going to be handled differently than our training data, and we will find that our training method won't generalize to that test data. Okay, so we have to use the training mean. We also have to use the training eigenvalues, or eigenvectors, and as well as the training singular values. So we want to use the training quantities when processing the test data. Okay, and then it's pretty simple. We fit our classifier. Now we give it these features, but here is the step where you can see that R is going to be a number. It's actually going to be within a loop because I want to test what happens for many ranks. And this is the rank of the approximation. So we're just going to use the columns. So the ZTR matrix contains the coefficients for all different possible ranks. And here is where we constrain them, and we use only the first little r, however many we want to use. And then to the test classifier, we just apply the test features, but again, constrained to R ranks. Okay, any questions on what we're doing here? Okay, so all right, so let's look at the results. So I'm plotting number of PCA components, which we called capital R in the lecture. And notice I'm doing this on a log scale. So this is like 1,000, 100, 10, 1. And looking at the test accuracy. So it's not monotonic as we might expect. Basically as we would expect, if we're using only like 1, 2, or 3 coefficients, test accuracy is pretty bad. And as the number of coefficients goes up, test accuracy increases. But then interestingly, for whatever reason, once you go from like 100 to 1,000, actually things get worse. Is West Water Street here? West, what do you have an explanation for what might be happening here as to why this is getting worse? Exactly, yeah. Maybe like these PCA coefficients, as the PCA rank goes up, these are the coefficients that have less and less to do with the samples. They're the ones that have the smaller and smaller eigenvalues, so they might just be like noise. And so we're seeing like the effect of some sort of model order selection. Like this maybe from a model order selection perspective is better. Here we've added a bunch of features that are mostly noise, so we're getting this overfitting. Okay, good. So now let's look at the runtime. And so here I'm plotting things on a linear scale and a linear scale just because it turns out that we actually have a linear relationship here. So as you increase the number of components, those are the number of features that XGBoost works on. You can see that the complexity grows linearly. So, twice as many features for XGBoost takes twice as long. It's a nice relationship. This is the runtime of XGBoost on its own, and then the orange also takes into account the runtime for PCA itself. And you can see that PCA, for this data set, for this size, is like a lot smaller than the runtime of XGBoost. So it's cheap to run PCA if it saves you on XGBoost's runtime. And you can see that, like for this optimal number of coefficients of 100, basically, I forgot to talk about this. This is the performance of XGBoost if you run it on the raw images. So if you run it on the raw images, you actually do better than PCA for any approximation rank. One of the things going on there is that, trees, well, actually all methods, not all methods, but trees certainly, because they branch on the raw features. If you transform all your features with this big rotation matrix, it's going to be a completely different tree structure. And so even if you run PCA if you run XGBoost using all the PCA coefficients, meaning there's no approximation in the data, but you've transformed the raw images by this big V matrix, you'll find that it doesn't ever do as good as running on the raw coefficients. And this just has to do with the fact that those raw coefficients are easier to build trees on, and than the PCA transformation coefficients. Okay, but that said, if you want to get close to that performance and reduce your complexity, this is pretty good, right? Because it's like, I don't know, maybe it's like 1/10 of the complexity to run PCA and XGBoost and get a pretty small reduction in the compromise on the accuracy. Okay, all right. Yeah, this is the runtime of raw.
What's the, wait, so if that's just, if the gradient is raw, what's just the blue line, just XG?
So I timed XGBoost in the loop, and then I timed PCA separately, so you could see like, so if this would be like the total runtime,
I see.
you know,
what you're saying.
then this is like, this much comes from PCA and this much comes from
Gotcha,
XGBoost.
the overhead of, yeah, I see what you're saying.
Yeah, there's not much overhead for PCA. XGBoost is really what takes most of the time
Gotcha.
to run this. Okay, great. Any questions? Yes.
So the dash orange line is without PCA, right?
Exactly, yeah. So this is like, I just ran this once, and it's not a function of the PCA coefficients, so I'm just kind of, you know, just, it's a constant value just for reference.
What if you had like a really noisy, grainy image, and then you use PCA just to pull out like the first, like almost as a way to remove noise? Would it still be worse than the original noisy image? Like training?
Oh, that's a good question. So you're saying like, you classify the noisy image and then you denoise it with
Yeah,
PCA and you
almost
classify
PCA.
based on that?
Almost use PCA as a way to get rid of that noise.
Yeah, you could definitely do that because you're right. What happens is, well, okay, but you have to be a little careful. It's like how are you gonna train PCA? Because if you give PCA a whole bunch of noisy images and there's really a lot of noise there,
The PCA itself will also be worse.
well, I think you'll kind of, I don't know, it might work. But basically, like, the idea that you're proposing of using like this low rank is actually a really good idea for denoising, and it is one of the main ideas for how, maybe not state-of-the-art 2025 denoisers worked, but if you go back like 10 years, it is one of the ways they did denoising. They did things with patches, but they kind of built up like little matrices, and then they did like an eigen decomposition, and they threw out the higher, the noise kind of fills up like these spaces that you can get rid of. And so a method like BM3D works very much like that. So it's a great idea for denoising. PCA itself, yeah, that's not going to be the best denoiser, but you know, it's a method we can talk about and derive in closed form.
So thank you.
Yeah. Okay. Any other questions? Yeah.
Yes. Here on this example, I'm just curious because X was between 0 and 1, right?
Yeah.
It was gray scale.
Right.
But if we have colors, it could be extended as well to PCA. The values are different.
Yeah. Okay. That's a good question. So when you have colors, you really have like kind of like three-dimensional data. You have like, you know, vertical, horizontal, and then color. Like you can think of your images as these 3D objects.
Yeah, like a code, right?
Red, green, blue is usually how it's done. So if you do this rasterization approach where you just like take that 3D thing and string it out into one vector, then basically you're going to get kind of like blocks of the red, green, and blue brightnesses. And all this will work the same without any change. It's just the dimension will be 3 times the grayscale dimension. And it will find out, you know, whatever redundancies you see across colors, and it will incorporate that as part of PCA. So nothing really changes, just the rasterization step. Yeah. Okay. Great. Okay. Any questions? Okay. So, all right, but I want to be a little careful in even suggesting to do this because PCA as an idea is not at all designed for classification, and I'll show you an example here where it completely fails. So PCA, you know, our objectives was let's make a linear method to reduce dimensionality of data, and let's have it focus on RSS because that's tractable, so we can derive everything in closed form. But when you do something like classification, you might get a situation like this. So here are the samples for class 1. And this is two-dimensional data, just to be simple. And then these are the samples for class 2. And if we're doing PCA, then there's only one option, is to reduce that to dimension 1. All right. So, all right, let me see. Is Spencer Munch here? No. What about, is Daniel Kowalski here?
Yeah.
All right, yeah. So what would be the PCA subspace in this case that we're projecting onto?
A line.
Yes. How is it oriented in the picture?
It's like, the x-axis.
A horizontal line?
Yeah.
No. No, it's not going to be horizontal line. Let me see. Is Frank Hegedus here? No. What about Brandon Gemperline? No. What about Luke Carter? All right. What do you think, Luke? So think again, like we're trying to find the line so that when you project the data onto that line, the projection error is best in terms of RSS. And the line has to go through the origin.
Yeah. So would it be like almost like a 45-degree line through the origin, like negatives?
Negative slope?
Yeah.
Exactly. It's a negative slope line. So it's like this. Because like essentially, if we're going to be representing our data on that line, you know, we get all our points are going to be here, right? And then our projection error is going to be like those things. And that is going to be better from the point of RSS. Sometimes when I ask this question, the students will respond this way. But you can kind of see here, we're projecting all the points onto here. And because these are farther, and because RSS squares data, it has a harder time. It really doesn't like to see these big distances. So that's why the PCA approximation is not that, but rather this. Okay, but now you can see what happens. So if we have this approximation, so all our red samples get mapped to this line, right? So there are all these red dots. But then all our green samples, they get mapped to this line. And now I'm going to be classifying based on these coefficients, the distances along the line. And you can see what happened to our data. Is it linearly separable? No, not once it's projected, right? So when doing PCA, we have actually thrown out all the information that told us class 1 versus class 2. And so basically we have completely killed ourselves. Like once we've done this, our classification is hopeless. So there are actually, people have thought about this problem. It's a kind of classical machine learning thing that people thought about like 50 years ago. And they came up with strategies that said, well, if you want to do this dimensionality reduction and you happen to know some of these labels, like the 2-in-1 labels, which PCA does not know about those, right? Doesn't know about those labels. Then it turns out that like this method called LDA, linear discriminant analysis, is going to do a smarter dimensionality reduction. And it is actually going to project everything onto this line. And when you do that, all your red samples are here, all your green samples are here, and it's linearly separable, and it's perfect. Everybody's happy. But of course, LDA needs to know about the labels in order to do that, whereas PCA doesn't have that information at all. Okay, so that's So this is, LDA, linear discriminant analysis, it's an alternate form. It is linear, like PCA. And it explicitly, says, once I do this reduction, I want the data to still, I want to be able to discriminate between the classes. So I'm not going to get into that method anymore, but if you want to read about it, you can click on the screen link. Okay, so this is the danger of applying PCA. If you want to do some downstream process that does not necessarily agree with PCA's rules for what's important and what's not important.
So would LDA also be better for like the image processing?
So LDA is specifically for classification, and it needs to know the labels,
Oh, okay.
right? So if we don't have the labels, then we can't use it. There could be other things we can use, and I'll talk about those towards the end of the unit, mainly for the purpose of visualization. But there definitely are much more sophisticated methods out there for dimensionality reduction that are not linear, that don't focus on RSS, but they exist. Yeah. Okay, so that's a good time. We will next talk about another interesting technique that's closely related to PCA, but a little different. But this is a good time to stop for today. So see you guys.